So let's talk about integrating products of powers of sine and cosine. And so you'll get a general expression that looks like this, and you have various kind of options there. So if m is odd, basically the term that's the power of sine, and positive, and n is any real number, then the strategy that you'd want to take is to split off a sine x from that term. So you'll be left with a sine of m minus 1, okay? And rewrite the resulting even power of sine, right? If sine was odd, then splitting off 1 will give you an even term. So rewrite the sine raised to the power of an even number in terms of cosine, okay? You could do that using the Pythagorean theorem and also half-angle identities, which we'll look at also. And then use u is equal to cosine x. On the other hand, if n is odd and positive, so the cosine term has a power that's odd, and m is any real number, then you split off a cosine and you do a similar thing with the resulting even power of cosine. And if both of these are both even and non-negative integers, then you use half-angle identities to basically reduce the powers of sine and cosine. Here are the relevant trig identities that we'll look at. So you have the Pythagorean identity, cosine squared plus sine squared is equal to 1. You also have these half-angle formulas, and it's a good idea to just memorize these. And as you could see, this term could be used to write cosines in terms of sines, and then these reduce the powers, okay? They'll reduce the powers of the sines and cosines. So let's take a look at a concrete example over here. All right, so let's see this example. So we have sine cubed x and cosine to the minus 2x. Okay, and of course we write the exponent with cosines and sines above the sine and cosine, even though of course you all remember that cosine ax, just what that really means is cosine x to the power a. It's good to keep that in mind. So let's take a look at what scenario we're in. We're in the first scenario. Okay, so the strategy we're going to use is to split off a sine x and rewrite the resulting even power of sine in terms of cosine, and then use a u substitution with cosine. Let's do that. So split off the sine x, and we're left with sine x dx. Rewrite sine squared x in terms of cosine. We're going to use the Pythagorean identity for that. And now we have a real power of cosine there. And use u substitution with cosine x, and so du is minus sine x. So the cosine to the power minus 2 becomes this u to the minus 2. The du will sweep up the sine x dx there, and we'll also have this cosine squared is u squared. Okay, and so you'll integrate these terms, and you end up with 1 minus u to the, so once you distribute the u to the minus 2 into this parentheses 1 minus u squared, you'll end up with this expression here, 1 minus u to the minus 2 du. Integrate that. Integral of 1 is u, integral minus negative 2 is plus 1 over u plus c, and then substitute back cosine and secant. And of course the secant is 1 over cosine, and so that's coming from there. And the minus sign that we had for the du resulted in this being written as 1 minus u to the minus 2. So if we would have distributed this u to the minus 2, this would, that product there is what would give you a 1. But you can see the 1 is positive in here. So we took care of that minus sign with the distribution. So let's take a look at another example. And this time we have sine to the power fourth cosine squared x. And let's take a look at what domain we're in over here. Okay, this is the domain of both being even. Okay, so we're going to use a bunch of half angle identities to reduce the powers of sine and cosine. Let's do that. So, okay, sine to the power 4 is sine squared, okay? And so we'll have a sine squared over here, and that's being squared. That'll give us sine to the power of fourth. But the sine squared we're going to rewrite as this, using what? The half angle identities, okay? Sine squared is equal to this, so we're going to rewrite it in terms of the cosines. So you'll have that squared term there. And the cosine squared, we also use the half angle identity, but with a plus sign there. And FOIL that out, okay, and you get this expression over here. For your cosine squared 2x term over here, you could again use a half angle identity and rewrite it in terms of cosine 4x this time, okay? And you'll also have a cosine cubed term. Okay, and how do you want to deal with the cosine cubed term? Well, that's a term where we're actually in the domain of n odd and positive m real. So we're going to split off a cosine and rewrite the resulting terms in terms of cosine. So let's do that. So that's the cosine squared. We split off a cosine, okay, and we get an even power of cosine. We write it in terms of sine, okay, and so you'll have 1 minus u squared over there, with u being sine 2x and du being 2 cosine 2x. You could see we could sweep up this term in the du up to a constant that we multiply by. And the rest of this we could integrate pretty straightforwardly. So they're all cosines here, and this, you know, we could take care of with the power rule and substitute back for u the sine 2x, make some simplifications, and you obtain your result there. Okay, so the idea there is to keep reducing the powers, the even powers, until, you know, if you do run into another strategy that you could work on, this cosine cube, for example, that was, we used another strategy for that because we had an odd power. You then followed the odd power strategy, and you continue to do this until you reduce down your cosine powers and your sine powers. So you continue to mix strategies until you've reduced them sufficiently. Now, that could be tedious and burdensome, so people have developed simple reduction formulas to deal with. So if you have a sine raised to the power n, regardless of, you know, it does have to be an integer, but regardless of the that, then you could reduce a positive integer. Regardless of that, you could reduce down the positive integer using these formulas, okay? And, you know, if n does not equal 1, you have these reduction formulas there, okay? So you could use these reduction formulas once you've gotten used to the integration techniques. So we'll emphasize here that n is a positive integer, so n is greater than 0 and n is an integer, okay? So it's in the natural numbers.